Yeah. Okay, let's get started. How are you guys? Doing well? Okay, great. Good to be back. So let's continue where we left off. I know I barely started the introduction to chromatography, and then Gary gave you the GC lectures. So I'm going to take a step back and finish my chromatography introductions, which is going to take today and the next 3 lectures next week to finish everything about on chromatography. By the end of it, you'll be chromatography experts. Great. So just to bring you back to what I talked about, essentially, was it last Friday? Yeah, it would have been last Friday. So first of all, define chromatography in one word. The challenge. Hey, Hallie. Separation, yes. And for separation to happen, what is the required one word? Challenging you on a Friday. No tired. Been a long week. Yes, Kevin. Affinity. Oh, Kevin gets +3. Make note of that. So yes, so you have to have an affinity to a medium. So the medium, remember we talked about a stationary phase, one medium, and then a phase that moves, the mobile phase. So you have to have an affinity to that stationary phase for 2 or more compounds to separate. And compounds will have different affinities to that, to the stationary phase. And if they don't have affinity, they won't separate. If you remember the justice example, if I take my daughter now to justice, neither I or her will have an affinity for the store. We will not separate, we will live together. So if I want to separate, I need to have an affinity and difference in affinity among my compounds. So that is a definite need. So separation, affinity. Okay, so can you remember some uses of chromatography? Now that you had Gary, probably he talked about a very valuable that you will be doing in the lab next week. Someone. Any idea? Next week. Have you been to Gary's lectures? Fatty acid composition. Okay, so that is one use for chromatography and specifically gas chromatography. So next week, half of you will be doing gas chromatography. You will be taking different oils and you will be trying to identify the identity of the oil. We will not tell you what oil it is. You might get a corn oil, you might get an olive oil, you might get an adulterated oil. Actually, each group gets all 5 oils. And you will want to identify based on the fatty acid composition using gas chromatography. So you will have triglycerides in each of these oils. You will have to, well, first of all, you have to break the glycerol of the fatty acid. And then you would have to methylate the fatty acid. Do you remember why we methylate fatty acids? It's kind of a brief revision of what Gary and I talked about. Why do we methylate fatty acids? What is a requirement in volatility? Thermal stability and volatility. So we want to make sure that we make our fatty acid volatile and thermally stable so that we can analyze them in the gaseous state. Okay, so we will de-acidify, that means we supplementer them, we break them down, and we take those fatty acids and we add a methyl group to methylate them. And then we separate them using gas chromatography, and they will have different affinity based on their difference in molecular weight, in their polarity, in their boiling point. And then we get separation of fatty acids, and then you will determine the fatty acid composition. You go to the USDA website, and then you say, okay, this fatty acid composition belongs to olive oil. So oil A is olive oil. It might be corn oil, don't write that down. A is so and so, and then corn, and then whatever of the different oils were. Anyway, so fatty acid, what else? Use it. The half of you will be doing something else in the lab. You remember I mentioned you briefly. You will be doing HPLC to determine. Anybody remembers? Yes, Stella. Thank you. I think I'm gonna go with +3 today. I have a good feeling about giving a lot of points. So +3 for Stella, whoever taking the participation. So yes, thank you. Caffeine in different beverages. We're gonna have a coffee. We're going to have a decaf coffee. We're gonna have a Pepsi. And then what else, Nigel? What other beverage?
Red Bull.
Red Bull. Yeah, we have one. Yes. Okay, so we're gonna measure caffeine and determine whether the caffeine that was either on the label or on the website for that particular beverage match what you get in that. Especially decaf coffee, is it really decaf coffee? So you would measure the caffeine content and see if that was a true declaration. Okay, so other uses we're going to apply chromatography throughout the semester. We're going to talk about using chromatography for vitamin analysis, using chromatography for amino acid analysis, using chromatography for carbohydrate analysis, using chromatography for contaminants of concern, like acrylamide, for example. So learning chromatography is very important at this stage because we will get a lot of application examples in future chapters. Okay, lots of uses. So in the analytical world, chromatography rules. All right. So I want to take a step back and explain extraction because the basis of chromatography stemmed from extraction. That means separating compounds in two different phases, liquid phases normally, and we do that for different purposes. One purpose is the actual means of analysis. A very perfect example that you will be doing in the lab is fat extraction to determine the fat content using organic solvents. So you will be doing two methods, one we call sausage, another we call mojo or mojolier in French, or just mojo as a name. So means of analysis. So we use solvent where we can extract the fat and weigh the fat so that we can determine the fat content. So actual means of analysis. Preliminary step, we're going to learn when you want to measure carbohydrate composition in a sample, you want to extract the fat first. First you dry and then you extract the fat and then you get to analyze your carbohydrates. So preliminary cleanup, sometimes you want to extract protein and produce a protein concentrate or protein isolate. We have to remove the fat first. So if you're working with an oil seed like soybeans, a lot of oil, so you make sure you extract the fat before you carry on with producing the protein concentrate or protein isolate. Concentration of the component of interest. You will do concentration of fatty acid in an organic solvent mixture so that you can analyze fatty acid. If you do flavor analysis, flavor is present in a very, very small concentration. So you want to use solvent to get it into another phase and have it concentrated so you can attack it with confidence. So the batch extraction, you have seen separately funnels before. I'm sure you did. Hi. Okay, so you use two immiscible solvents and you separate your components in two phases. Very easy. You shake, you wait to settle, and you hope that you don't form an emulsion, and then you separate the phases. A better way of doing that is continuous or semi-continuous extraction. We're going to learn about continuous and semi-continuous extraction in the fat analysis lab or lecture, where you have your solvent here and you have your sample in a compartment here, and you heat. The organic solvent evaporates, goes up into a cooling, circulating, cold water, so cools it down into the sample, solubilize the fat or whatever components you're interested in, and siphons back into this original container. So we'll learn about that method. Now, the countercurrent extraction, which I will show you a demonstration here in a bit. The countercurrent extraction, that's the origin of chromatography, liquid chromatography. So that's where chromatography came from, especially what we call partition chromatography. When you see the word partition, it's for liquid chromatography. That means you have your both phases, the stationary phase is liquid, and the moving phase or the mobile phase is liquid too. So that's your components that you want to separate are really partitioned or distributed. Okay, so you can call it partition or distribution. So it's partitioning between these two phases. And you have at equilibrium, once they are partitioned and you reach equilibrium, you have a partition coefficient, which is a constant. I'm not sick, it's just from the procedure, I have a itch here. So, okay, the concentration of solute in phase 1. Phase 1 is your mobile phase, the phase that is moving. Phase 2 is your stationary phase, the phase that is not moving. Staying put, and I'll show you the demonstration. Here, solute A is more soluble in phase 2. That means it likes the stationary phase better. Solute B likes the mobile phase better. So it's going to move quickly, more with the phase that is moving. Okay, so who will have a higher, or which of these solutes will have a higher partition coefficient? A or B? Yes.
B.
Huh?
B, because
Yes.
it will have higher concentration in its market.
Yes. So B is going to move faster and have less affinity to the stationary phase, and then will separate and leave faster than solute A. And I will demonstrate this. Okay, let me escape this here and go to this. This guy here is the guy that came up with this extraction technique. We call it countercurrent extraction. So I'm going to start it over. Restart. And we see B, like I said, has a higher affinity for phase 1, which is the moving phase. Okay. So this liquid here is your stationary phase, phase 2. So it's present in all of these tubes. So this is one tube. and you want to imagine, not imagine, visualize the different, each compartment is a tube, okay? And you shake, and this moving solvent will be dispensed in the next tube. You shake and so on. So I will hit start so you can see. Start. Extract. Okay. So shaking, I have these two compounds, B and A. The B is the red, pink, whatever, and the A is the green. So transfer. So you shake, you transfer. So you see the green likes the stationary phase better. So you see it stayed more behind. And the red or pink like the moving phase, the mobile phase. So you see more of it in the second tube, but they're not yet separated. Then I extract again and move to the next tube. And then we start seeing less and less green, so less here in comparison, more of the pink here. So B is this one. But they are still somewhat not separated. So I extract again and transfer. And I repeat. So the more tubes I have, the better is the separation. So the longer the column, if I'm doing column chromatography, the better is the separation. Okay, so extract, transfer. I keep doing that multiple times, and I see almost two separate peaks. In chromatography, you would see peaks. And the more you do extraction, the more you see separation. And if you keep doing that, B will be, at the end, you collect B, and then you get another tube to collect A separately. Then you would have separated these two compartments. So far, look, eluted meaning left the tubes or left the column. Okay, so now both of them are still in the tubes. So if I continue with that, I will eventually see some of B starting to come out, to leave basically. So now you see here the percentage, B is coming out. I'm collecting B, and then I will start collecting. I almost have perfect separation. Sometimes I have residual of B with the A and residual of A with the B. But again, the longer the more tubes I have, the more separation I will get. So almost now I have over 90% with a little bit of A, that's the impurity here. And then after A is B completely extracted, I can change my tube and now I have collected all of B. I can remove that and bring a fresh tube to collect all of A in it. So you get the idea, you get the gist of it. They're partitioning, they're separating based on their affinity, the different phases. That's the idea of chromatography. And with that, going from extraction using a tube, you extract or you separate using a chromatographic, mostly either column, or we're going to introduce also paper chromatography and thin layer chromatography as planar chromatography. But most of what you will see later on in application, it's column chromatography, where you have a column, you have a medium in there, your stationary phase, and then you have a mobile phase. Okay, You get the idea, huh? All right. Okay. So this is basically the unit, the different tubes, shaping and the transfer into the next tube. The more tubes you have, the better separation you get. Okay. So you will hear several terminologies, and I want you to be familiar with them, because when you have a question in a quiz or an exam, you might be asked what the stationary phase is. In this example, you want to know what I mean when I say stationary phase, when I say a solute, when I say mobile. So the solute is the component that is soluble in one of the phases. So the solute or solutes are the components that you want to separate or detect or quantify. So you want them to be miscible in one of your phases, basically. Stationary phase, it can be a liquid or a solid. That means the phase that doesn't move, okay, that stays in its place. So either your column with the media inside of the column, or that liquid in one of the tubes, or in the tubes that don't get transferred. So the mobile phase is the phase that goes through your stationary phase and carries or helps separate the components. So we call it eluting solvent, eluting, that helps the components to elute or leave the column. That term of elution meaning leaving the column, okay, leaving your medium, leaving your stationary phase. In gas chromatography, it's called carrier gas, like helium, for example, is inert. It carries the evaporated components. And supercritical fluid, we'll introduce it briefly. It's a chromatography where you use a gas like CO2 in the liquid phase, above pressure and temperature, above the critical pressure and temperature that makes the CO2 in gaseous form. You turn the CO2 into a liquid form. And we'll talk about that later on. Series of equilibration. We're going to talk about how do the components separate in a column or in a stationary phase. They go through a series of equilibrium between the stationary phase and the mobile phase. So the series of equilibrium that happens, if you want to imagine and remember those tubes, you shake, 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 you have an equilibrium and separation. And then you transfer, shake, you wait for the separation to happen, and then you transfer. When you wait for that separation to happen, you're waiting for an equilibrium to occur between the two different phases, where the partitioning reached equilibrium and there's no longer a change. The eluent is the eluent that you would use to elute. And the elute is a verb. So the eluent is a noun, the elute is a verb. So just get familiar with these terms because you will see them a lot. You might hear me talk about them a lot. And then we'll talk a lot about chromatographic peak. So when we run chromatography, we have a detector. And the detector gives us a signal, either an absorption or, for example, in gas chromatography, you will probably, you already know about flame ionization detector, which you will be using next week. You would get a signal of the ions, the conductivity of the ions. So the signal is in the form of a peak. And the area under the peak is what we relate to a concentration of the component. So we will talk a lot about chromatography. Okay. So chromatography, we already defined it. It's a separation technique. We use it a lot in food analysis. And it's based on the partition, if you have liquid, or the distribution, if there is solid liquid or gas liquid or gas solid. So partition always means two liquids. The stationary phase is liquid, the mobile phase is liquid, and it's partition chromatography, and then you have a constant. It's based on the concentration in the mobile phase, which is phase 1, concentration of the solute in the stationary phase, which is phase 2. Okay. So you have different types of chromatography. So when I give you an example in a quiz and ask you what type of chromatography would you use, I'm asking you to tell me, oh, I'm going to use gas chromatography, or I'm going to use liquid chromatography. So when I ask you what is the type, that means, is it gas chromatography? Is it liquid chromatography? And then in liquid chromatography, we're going to talk a little bit about planar chromatography, where we use a paper or a thin layer chromatography. And then we're going to talk about column chromatography, the use of a column, and that's the most common tool that we are going to have many examples on. So the other thing that you need to learn is gas chromatography. When we say gas or liquid, your mobile phase is either gas or your mobile phase is liquid. So GC, gas chromatography, that means your mobile phase is gas. Liquid chromatography, your mobile phase is liquid. And then in gas chromatography, it used to be called gas liquid chromatography. Why? Because oftentimes you have a solid impregnated with a liquid as your stationary phase. But sometimes you only have solids, but in most modern gas chromatography column, it's really a liquid bound to a solid. But we don't call it gas liquid chromatography, we call it gas. In liquid chromatography, the planar, both paper and thin layer are partition. They're always the paper or the thin layer chromatography, there is an impregnation of a liquid phase on that solid, the paper or silica in the case of thin layer chromatography. So water, let's say, is impregnated, so water becomes your phase 2, which is the one with the stationary phase. And then there will be another liquid as your mobile. So it's always liquid when it is paper or thin layer. When it's column chromatography, sometimes your stationary phase is solid. Sometimes the stationary phase is liquid, which means the solid, you use a solid as a holder for the liquid. You impregnate a solid that is inert, you impregnate it with a liquid, then your stationary phase is liquid. And then you will have the mobile phase. So in column chromatography, we're going to talk about examples of liquid, and we're going to talk about examples of solid. So in column liquid chromatography, which is a lot of the focus of my chromatography section, Gary already talked about gas chromatography. In column liquid chromatography, we have a category of its own, size exclusion. This chromatography you don't have a bonding or interaction of your components with the stationary phase. The way it separates based on the size of the pores of your stationary phase. So the compounds separate based on size only. In partition or absorption chromatography, they separate based on their interaction, their physical or chemical interaction with the phases. So basically, liquid-liquid or liquid-solid, and the compounds interact differently with the two different phases, and thus they separate. Again, if they have the same affinity, they will not separate. And if you have molecules of the same size, they won't separate. Under column liquid chromatography, both in the partition and in the partition phase, I would say, you have reverse phase and you have normal phase. So in normal phase, I will talk about it more in detail, but just quickly, remember that the stationary phase will be polar. And the mobile phase is non-polar. That's normal. So if you have two compounds, one of them is more polar than the other, the more polar compounds will retain longer on top. The less polar compound will move faster because the mobile phase is non-polar. That's normal phase. Reverse phase is the opposite. And the only reason this is called reverse phase is because they discovered, or they worked with normal phase first. And then they discover, oh, we can reverse it. We can make the stationary phase non-polar. And then we can make the mobile phase polar. We can reverse it. And that's why it's called reverse phase. There's no other scientific reason. Then under absorption chromatography, you have hydrophobic interaction chromatography, which we will talk about. Interaction with the column is based on weak hydrophobic linkages. We have affinity chromatography, which the interaction is very, very specific, like antibody to an antigen, or an enzyme to a substrate, or an enzyme inhibitor. Very, very specific interaction. So if I want to purify a very specific protein, say an allergen, and I want to purify it and detect it, I will use a column impregnated with antibodies specific to that particular protein, that antigen. So it would be a very, very specific. If I want to purify an enzyme, I will use a chromatographic column impregnated with enzyme inhibitors. So they will bind very specifically to my enzyme, and I can collect it in a pure form. So affinity chromatography is as absorption, because the compound is going to absorb to your solid phase via molecular interactions. So hydrophobic interaction and affinity are modes of separation under absorption chromatography. So when I ask you about mode of separation, I mean, are we using reverse phase? Are we using normal phase? Are we using affinity chromatography? Are we using hydrophobic interaction chromatography? Or are we using ion exchange? All these three are under absorption because the components are going to absorb onto the stationary phase via molecular interaction. When we say ion exchange, that means the interaction is based on the charge. So you will have like a negatively charged stationary phase will attract positive charge components. And we call this cation exchange chromatography. You don't have to take a lot of notes now because I will be talking very much in detail about each one of them. So what I want you to remember from this slide is that affinity, ion exchange, hydrophobic interaction, they have the same color as absorption chromatography, the circle, the same color, because there are subsets of liquid solid chromatography, absorption chromatography. Because the components that you want to separate, they absorb on the column via different interactions, either hydrophobic interactions, ionic interactions, or very highly specific interactions. This is a good study table. You'll find this in chapter 12, table 1. So here, you have the method or the type of chromatography. So what does it mean when we say gas liquid chromatography, your mobile phase? I might ask you in an exam, what's your mobile phase? Mobile phase is gas. And stationary phase is liquid, gas liquid chromatography, gas solid chromatography. How do we, what is a retention? Retention meaning the retention of the compounds on your stationary or on your column. So the retention or the interaction or the affinity to your stationary phase varies in gas chromatography based on molecular size and polarity. And molecular size and polarity determine boiling point and the evaporation point. So they separate accordingly. You'll learn next week and the week after in lab that different fatty acids have different molecular weight, different polarity, and therefore different boiling points. So they will separate on the column according to these properties. Supercritical fluid, again, same thing, your stationary phase, your mobile phase is supercritical fluid, and your stationary phase is solid, and then how they are separated based on what characteristics. So we're going to talk about, I'm going to explain supercritical very briefly, but I will spend more time explaining those different modes of separation. But this is a good review to understand what the mobile phase and stationary phase for each of these different types or methods of separation. And then how do they separate based on what type of characteristics, physical, chemical, or molecular characteristic. You already took 2 lectures on gas chromatography. In previous years, I just give an introduction before Gary gets into his 2 lectures, but this is a refresher. Here we have a system where you have a flame ionization detector. So we need hydrogen and oxygen to generate the flame. We have an oven which gets heated over time. You can ramp up the temperature or you can keep the temperature stable. And then you have the column has a very long capillary column. And then you have the carrier gas, which is really in this case an inert gas that will not interact with your components. And you have the injector, where you inject your sample. So the separation is based on the thermal stability of volatiles. So when you generate the fatty acid, you want to methylate them so that they are thermally stable and they can become volatile. If they are not thermally stable, they're going to degrade at high temperature. If they cannot volatilize at the temperature that you can put the oven to, then they won't evaporate, they won't be carried in the gas state, then they cannot be fit. So it's very important in gas chromatography that we derivatize. So derivatize meaning you take your component or compounds and add to them a certain group that helps them become thermally stable and volatile. So you will hear the term derivatize in later chapters when we want to evolve gas chromatography as a method of analysis. Sometimes you don't have to derivatize, so flavor compounds are naturally thermally volatile compounds. So that's why in the flavor analysis, it's almost always gas chromatography and you don't need the filters. So you build a controlled temperature gradient in the oven, so that means the temperature builds up over time. And then your volatiles are separated based on their molecular size and polarity, and molecular size and polarity determines the boiling point. As I say. Okay, we'll keep the recap till next time. I'm going to continue here. Liquid chromatography. So we will talk from now on only liquid chromatography. So we have paper chromatography, which is one example of a planning chromatography. Who has used paper chromatography in the past? Is it in school or a lab? So you've seen it, right? So paper, basically your support is a cellulose matrix. So paper is made up of cellulose. So the cellulose in this case only is used, or what happens, the function of it is only support. Because then you would have an impregnated water. So you take your cellulose and you wet it with water. The hydroxyl groups of cellulose interact with water via hydrogen bonds. And then the paper becomes all wet. And that would be your stationary phase. Water will be your stationary phase. And water is immobile. So it's not moving, it's your stationary phase. And then what you would do is, we normally measure a centimeter or an inch with a pencil and a ruler, and we put a dot with a pencil, and we put a marker, we put our sample, 1, 2, 3 samples, different samples that have different components. And once I put my samples, dot my samples, I put it in a chamber. And this chamber has a solvent that is immiscible with water. Let's say hexane, chloroform, diethyl ether, petroleum ether. These are all immiscible solvents in water. So what happens, the solvent is going to start moving up, the little forces. So it's going to move up. And the components in my marker and in my samples are going to start moving as well. Okay, so if my mobile phase is organic, non-polar. So the yellow dot here and here, is it the least polar or the most? Think about it. That's 5 minutes. Yes.
Would say the least polar?
The least polar, yes, very good. So since I only have, every time there's only one person that raises their hand, will get +3 today. I don't know why I feel that way. It's not going to be the same way. Word. I don't feel that way every day with us today. Okay. So the least polar, because your mobile phase is non-polar. So the polar compounds want to stick with water. I don't want to. I really don't like that solvent. I'm going to take my time with me. Whereas the components that are less polar, oh, I like this hexane, or I like this chloroform, I'm going to move up with it. So they separate based on polarity. Is this normal phase or reverse phase? Thank you for answering, but no, it's normal phase. Who answered, Carol? Yeah, but she still gets +3. I mean, for courage, no? Answer is an answer. Okay, so what was my question?
It was reverse.
No, it's not reverse. It's a normal phase. You will learn reverse and normal. They're confusing because they're opposite to each other. So whenever the water or the polar component is stationary, not moving, that's normal. When your non-polar is stationary and not moving, that's reverse. You just have to remember it that way. Think of water and say normal. Water is normal. Hexane is not normal. But just, anything that will make you remember or help you remember normal versus reverse. So the most common example that people give is the separation of amino acids on paper chromatography. You have a mixture of amino acids. They differ in their polarity. You can visualize them using paper chromatography. Another example for using paper chromatography, which I have here, separation of saccharides. Another one is separation of pesticides, for example. It's a qualitative measure of whether or not pesticides are present or what type of pesticides. As a qualitative measure. So this example, the amino acid separation, ninhydrin is the reagent that you use to spray after separation. So once your solvent reaches the top to a certain point, you take that paper out. You won't see your sample visually. You won't see the components visually. So this, you spray with the reagent that interacts with amino acid and give you a colored compound, which you can see. In case of sucrose and glucose, you can visualize by autoradiography. In case of, fatty acids or fat, different types of fat separation, you also use a different reagent you can burn with the acid, like H2SO4, you can burn. And then you can see burnt spots. Okay. You can have this method in 2D, two-dimensional, meaning you choose one phase, and the sample is here, and you get components separated. You can see that some of the components are partially separated. So you have these two dots not separated well, these two dots not separated well. They have close affinity to the mobile and the stationary. So their partition coefficient is very close to each other under these conditions. So after you develop, you take it and then you put it in a different solvent. So you put a completely different solvent. Let's say you started hexane, you go here with diethylene, for example. You flip it, and then you run another separation. You can see that the blue and the yellow separated, the orange and the pink separated. So these have different affinity for this particular solvent. So sometimes you need two-dimensional separation to get perfect separation, especially when compounds have similar molecular properties. Yes.
I have a question. Is paper chromatography the only chromatography that doesn't measure from peaks?
You don't get peaks, you get spots. And I was gonna go next to show you what you measure. In this case, you don't have a peak, you measure relative mobility factor. And that's how you characterize the different components. So we're running out of time, so I'll explain that.
Is it just the only one that doesn't have the peaks out of all the
This one and also liquid thin layer. Okay, I'll see you on Monday. Have a great weekend. Yeah, 7:35.